Let's knock out a couple problems from chapter 12. I almost said chapter 60. These will be two static equilibrium problems in which you have to apply the conditions for, you guessed it, static equilibrium. And this first one's not very difficult because there are no angles in this problem other than 90, and that makes the calculation of R perp really easy. So there's a kid walking along a beam here. The beam is supported by two posts, and the beam is not attached to the posts. So there's no bolts, screws, or glue here, which means if this kid were to jump up and down on the end, he could probably make the whole thing tip and even fall off. So we're supposed to figure out, given the fact that the beam has a mass of 40 kilograms, the kid's just 20 kilograms, and the beam is 5 meters long, and also the two posts are separated by 3 meters, how far out can this kid go before this thing starts to tip? Now, depending on these parameters, we could get a variety of answers. If this beam were really heavy and it was already in equilibrium before the kid got on it, you can imagine that this kid might be able to go all the way to the edge and it still wouldn't tip. You know, if his mass is insignificant compared to the beam's mass and the beam is already in equilibrium, maybe he can even jump up and down and it's not going to tip. And if that were the case, then the value we would find for X would probably come out to be a negative number, indicating that he could go all the way out here before it started to tip, because I'm measuring X positive this way. And I'll point out, I'm setting this up differently from the way your solutions manual did so that you can get practice seeing things done different ways. Remember, one of the first things you should do when you solve a torque problem or a static equilibrium problem is to choose your origin. Your book chooses to put the origin right here. So they calculate torques about the point of contact between the left beam, or excuse me, the left post and the beam. Let's think about it conceptually that way. If you're imagining that the beam is about to tilt or pivot about this point, let's look at the various torques. And here's where I will draw the forces I can find. And remember, in a torque problem, it matters where you put the tail of the vector. Previously, before chapter 12, we didn't care about that. Now, you really need to draw the vector so that its tail is at the place where the force is actually applied. And the force on what? Sometimes it's so obvious you almost overlook it, but what we're really talking about here is the beam itself. Since we're looking at the point at which the beam tips, we're looking at the conditions for static equilibrium for the beam. So I see 1, 2, 3, 4 forces on the beam. First of all, the beam has weight, and that means gravity is pulling down at its center of mass. Remember, as far as gravitational torques are concerned, you imagine that the full weight of the object is applied at its center of mass. So I'm going to call this Fg. Oh, you know what? I'll go with the W for weight. Let's do that. WB, not Warner Brothers. That's the weight of the beam, and it's applied at the beam's center. Now, if this is 5 meters long, this would be 2.5 meters from here. And let's see, if this is 3 meters and this is 2.5, then this distance would actually be 0.5 meter. I'll just label that now because we may need it. And what is the direction about this origin due to the torque from the weight of the beam? Well, of course, gravity would tend to pull the beam this way. So there's a clockwise torque about this origin from the weight of the beam. And then don't forget that this post here is pushing up on the beam. There's a contact force between the beam and the second post, and I'll call that F2. I could have called it N2 for like a normal force, but I believe your solutions manual went with F1 and F2. So then I'll call this F1. And what direction is the torque about this point due to this force? Well, the post here pushing up on the beam would tend to rotate it counterclockwise. So that torque helps balance the downward torque from the weight of the beam. What about the torque from this force about this point? Remember, any force that passes through your origin has a lever arm or a moment arm of 0. That means no torque. So if we were to compute the torques about this point, we would not even need to include the force F1. Okay, I mentioned that there are 4 forces. What's the one force I'm leaving out? Well, that would be the contact force between the kid and the beam. Now, since gravity pulls the kid down, the beam would have to push up on the kid to keep the kid in equilibrium. And if the beam's pushing up on the kid, that means the kid is pushing down on the beam. So here's the force that the kid exerts on the beam. And I'm going to call that WK for the weight of the kid. Because if you were to apply Newton's second law to the kid, you would see that the beam has to push up on the kid with a force equal to the gravity force on the kid. That's what I call the weight of the kid. Okay, Newton's third law was just used there. Okay, so your book computes torques about this point, and that means they've got a single counterclockwise torque, that's this post, having to balance the two, did I say clockwise or counterclockwise? This is the single counterclockwise torque, which has to balance these two clockwise torques in order to keep the beam in equilibrium. But for practice, let's do it differently. Let's put the origin here. So I'll put a big old dot indicating the origin of my coordinate system. And now, because force F2 passes through this point, the torque due to that force is 0. And I'm just realizing that this choice of origin is going to give us trouble in a bit. But that's good. That's instructive. You'll see why sometimes you do have to choose the, quote, correct origin. Okay, let's start with the sum of the forces in the y direction need to be 0. That's one of the conditions for static equilibrium. I see F1 and F2 up. I see the weight of the beam and the weight of the kid down. Those have to sum to 0 if the beam is in translational equilibrium. So now we know that the upward forces together have to balance. And then weight, isn't that mass times g? So I'll take the total mass of the beam and the mass of the kid, and multiply it by g. Okay, so since we're given these masses, if we can somehow figure out what one of these forces is, then we will know the other force. I'm gonna leave that there. Now, the other translational equilibrium condition, this is a trivial condition for this problem because I don't see any forces in this direction. So if I had plugged in the net force in the x direction, I would have 0 equals 0. That tells us nothing. No information can be obtained from that equation. So we move on to the third and last equation that we have at our disposal for these static equilibrium problems, and that's the one that says that the net torque needs to be 0. Okay, about this pivot point or origin, I see a clockwise torque. Right? If you think about the kid pushing down on the beam, and I'm assuming he's past the post. He's got to be already past the post if this thing's about to tip. He would be exerting a clockwise torque. His weight tends to make the beam tip this way. And the pull of gravity at the center of the beam would tend to pull it back the other way. See that? So the direction even of a torque depends on your choice of origin. When I put the origin here, as the solutions manual did, we would say that the torque due to the weight of the beam is actually a clockwise torque. But now, when I evaluate torques about this pivot, I find that the weight of the beam would tend to rotate the other way. And maybe you're thinking, wait a minute, if this thing's going to tip, there's a definite direction in which it will tip. Yes, that's true, but that's kind of irrelevant to the torque equation. You can imagine that it might be free to tip in either direction. If it's going to be in equilibrium, the sum of the torques have to be 0. So you don't actually have to know which direction it would tip to enforce this condition for static equilibrium. That's a subtle point. Like, you could evaluate the torque equation about a pivot that makes no sense physically and still arrive at the correct answer. I could have put the origin out here and evaluated the various torques, and I think that would still lead to an answer. I'm not going to check that, but you're welcome to do so. Okay. Now I'm going to use, for this problem, I'll use torque equals R perp F. Let's use that formula because do you notice that every one of these forces is perpendicular to the so-called R vector? Like if I draw the R vector for the kid, I've given the beam a finite thickness here, but we're supposed to imagine that it's very thin so that the vector that points from my pivot to where that force is applied would be this vector right here. It's hard to see there. This goes from the pivot to where the kid's weight is actually applied to the beam. And that vector is perpendicular already to the force vector. And that makes it really easy to visualize R perp. You know, if you wanted, you could extend the line of action of the kid's weight. And it's obvious that this distance is R perp, right? It is the perpendicular distance. It's not going off like this or this. It's already perpendicular. And the same is true for all these forces. So that's why this problem is not particularly difficult. The evaluation of the torques is relatively straightforward. Okay, here's what I'm going to do. I am going to acknowledge that the torque due to F2 is 0 because it passes right through the origin. And that means I have only got 1, 2, 3 torques to worry about. So I'll say the torque due to F1 plus the torque due to the weight of the beam plus the torque due to the weight of the kid must equal 0. And if these are supposed to sum to 0, that means one or more of them must be a negative torque. And that means we just have to figure out whether each torque is clockwise or counterclockwise. So yeah, technically a torque is a vector. And if you want to talk about components of a vector, you need subscripts X, Y, and Z. And I'm not doing that here. So it's implied here that these quantities can be negative. Okay, let's go a little, I'm going to do more or use more detail here than I normally would because we're just getting practice with these. Since each torque is R perp F, that would be R perp for the force F1 times the force F1 plus R perp for the weight of the beam. So I'll put it R perp B. That means that's supposed to say R perp. This is R perp for the beam times the force, which is the weight of the beam, plus R perp for the kid times the weight of the kid. I ran out of room. That's got to equal 0. So I'm just reminding you that each torque is computed as a lever arm times a force. Lever arm times a force. And for these two forces, we just use the weight of the beam, weight of the kid. Now, the one thing I'm missing here is the assignment of minus signs, because for me, the notation that I use, R perp is always a positive quantity. So I have to figure out which of these torques would be negative about this pivot. Well, you just have to use your common sense. If you could tip this beam about this post, what would be the direction of the torque from this force? Well, pushing down on the right side would tend to make this rotate clockwise. So I know that the kid's torque is negative, and I really should have put a minus sign right there. Same with F1, is it not? If this post is pushing up on the left side of the beam, that would also tend to make the beam rotate clockwise. So that is also a clockwise torque, so I give it a minus sign. In fact, the only positive torque, the only counterclockwise torque would be the one from the weight of the beam. Gravity's pulling right here. That would tend to make the beam rotate this way about this pivot. So that's the one that gets the plus sign. And now let's evaluate the R perps. And this is where my choice of origin made it slightly more complicated. Your book's choice of origin over here made it easier to evaluate the R perps. Okay, so what is the distance from the pivot to the line of action of F1? Well, that's not so hard. That was given to us as 3 meters. That's no problem. So I'll say negative 3.0 times the unknown force F1. So this is R perp for the force F1. It's the distance from the pivot to the line of action of F1. You can see that 3 meters there. And then for the beam, okay, well, that gets a plus sign. That's why I needed this distance here. The ½ meter is the distance from the pivot to the line of action of the gravity force at the center of mass of the beam. So I'll say plus ½ meter times the weight of the beam. Yes, the weight of the beam is the mass of the beam times 9.8, but I don't have to evaluate that yet. Minus, and then the last one, okay, this one's a little annoying. Here's how we're gonna have to do it. We need this distance right here. This is from the pivot to the line of action of the kid's weight. Well, if we could take this distance from the pivot to the right side of the beam and subtract this unknown quantity x, because that's what they're asking for. How far from the end can the kid be when this thing actually tips? So let's take this distance and subtract x, and that would give us this. Well, if the whole thing is 5 meters, if this is 5 meters long and this is 3, then we're talking right here about 2 meters from pivot to the end of the beam here, 2 meters. So 2 meters minus x would give us this. 2 minus x times the weight of the kid, and that's got to equal 0. Okay, so I've now written 3 equations. This one, this trivial one that says 0 equals 0, and lastly, this equation. And what I'm solving for is x. So we only have one unknown. Can we solve for that? Oh, I take that back. There's only one unknown that we're interested in, and we have 3 equations to work with. Well, how many unknowns are in that equation? We're given the masses. Those are known, but we don't actually know F1 or F2 or X. Can that be right? Huh. Hang on a second here. Okay, I got tripped up for a second because there's actually another condition we have to enforce in this problem. I know that ahead of time, and I have not yet written that condition down, but I was thinking, wait a minute, we've got 3 equations and 3 unknowns. We can already solve for those 3 unknowns, but I am mistaken because this is a trivial equation. It doesn't actually give us any information. So really, we only have 2 equations to work with, but we do have 3 unknowns, F1, F2, and X. You cannot solve 2 equations for 3 unknowns. So we do need a third condition. And this is where you acknowledge the fact that at the tipping point, because that's what they're asking, how close can you get to the edge? Right when this thing starts to tip, of course, it's going to tip about which post? This post, which is the nice thing about making this your choice of origin. You know, your book used this as the pivot point, even though that's not really the point about which this thing will actually tip if the kid goes out too far. Now, that doesn't matter. You can still get the same answer that way. But my choice has the advantage of using the actual pivot point as the origin. Okay, so when this thing does start to tip, then the left end of the beam has just begun to lift off of the left post, and that means F1 goes to 0. So that's our third condition. We'll use the fact that F1 is 0 at the tipping point. So that means we can go back here and say, okay, we now know that F2 alone must support the entire weight. Makes sense, right? If this beam is just starting to tip, then all the weight is resting on the second beam. So it has to push up with a force equal to the combined weight of, did I say beam or post? I meant to say post. It's all the weight is on the second post. So the post has to push up with a force equal to the combined weight of the beam and the kid. Okay, so that means we can plug that into this equation. We know what, okay, so perfect example of what I was getting at earlier. See, we don't even need that, interestingly enough, F2. Because of my choice of origin, F2 is not even necessary. The fact that it supports the whole weight is not necessary, because check it out. If I look at this equation now, the torque equation, this equation alone is sufficient to find X, because if the beam has just started to tip, then F1 is 0, and I have a single relation involving the weights of the beam and the kid and X. Okay, so because of my choice of origin, I did not even need the translational equations to get the answer. I kind of got lucky in that sense. Now, the price to pay was that the determination of the distance was just a little more difficult. So there's usually more than one way to get to the answer. I'm not going to say that any choice of origin will work, because sometimes the choice of origin will eliminate from your torque equation the one quantity that you're actually looking for. And then you would have to go back and choose a different location. And I thought that's what was going to happen here, but I was mistaken. In fact, it was actually easier. Okay, so let me rewrite the torque equation with this added constraint that the force F1 of the leftmost post on the beam is 0. Okay, so I've got 1/2 meters times mass of the beam times G. I'm now evaluating the weight of the beam in terms of its mass. And I'll put the other term on the other side, equals 2 minus X times mass of the kid times G. So here's the single equation that we need to figure out how far from the end he can go. And I should also point out, I don't think I said this, the book used X differently. They used X as how far out the kid can go with respect to the post, and then subtracted that value of X from the 5 meters to find this. I'm just calling this distance X directly. So I would, if I were you, I would read through the book solution as well to see an alternative way of solving this problem. Okay, well, the G's go away, and I'll divide on both sides by the mass of the kid. I don't usually show these steps. So I get the 2 minus X is equal to, let's see here. I would have 0.5 meters times the mass of the beam, which is 40. And then I would have to divide by the mass of the kid, which we're told is 20. So I find that 2 minus X is equal to 1. That seems kind of suspicious. Did I do something wrong on my calculator? Half times 40 is 20. Oh, that makes sense. Okay. So solve this, and of course you find that X is 1 meter. I find that the kid can go out as far as 1 meter from the end of the beam. Now, does that mean we drew our picture correctly? Because if this thing is 5 meters long and he can be 1 meter from the end, then he's out at the 4 meter mark. So he is in fact past the post. And this is kind of interesting. If I had found that X was, let's say, 2.5 meters, if he could be 2.5 meters from the end, 2.5 would put him right in the middle, which is actually on the other side of the pivot. And that would be problematic because that would mean that I had chosen the sign of his torque incorrectly, right? If the kid was over here, wouldn't the torque from the kid actually be counterclockwise? And that would mean that I had written my equation wrong. That would be problematic because it would have led to the wrong answer. So good thing our guess was correct, that the kid has to be past the post before this thing starts to tip, okay? 3 conditions for static equilibrium. You write those down. It becomes an algebra problem. The challenge is often visualizing the torques. Now, what I didn't do for this problem was to do a simpler diagram. What you could have done is just draw a single horizontal line to represent the beam and get rid of the clutter in the problem. Once you've chosen, if you had chosen this as your origin, you could put a dot there. You would draw the various forces. This is the weight of the beam, the weight of the kid, F2, F1. And by uncluttering your diagram, it can make it a little easier to determine the torques. Of course, this looks pretty bad, right, with the ink bleeding through. Here's another static equilibrium problem from your homework that presents different challenges. We've got the wall of a building here, outside wall of a building, and a rod or pole sticking straight out from the building from which we'd like to hang a signpost. So, of course, we need a cable to support the weight of the pole. Otherwise, the sign would well, I take that back. If you didn't have a cable and this were made out of something particularly rigid like steel, you probably could support the weight of the signpost, but over time, the rod would tend to bow and eventually it might break depending on the weight. So this cable is here for support. That's actually something that we do not look at in this class. It's probably very complicated to talk about the stresses within a beam due to its own weight and the amount by which it would flex. I'm sure that's something that you'll learn about in a future class if you're going to get a degree in civil engineering, because you're talking about buildings and stability of structures. You would be applying a lot of the stuff we talk about in this chapter, but going much further. So we just pretend everything's perfectly rigid, and we don't worry about that sort of thing with these static equilibrium problems. So the question is asking, given the fact that these dimensions are as stated, and that the left edge of the sign is 80 centimeters from the wall, how massive can this sign be without the string breaking? Because we're told that the string cannot have a tension any greater than 300. After that, it'll break. And yeah, I'm realizing here that depending on how rigid that pole is, you wouldn't necessarily even need the tension at all. So did they even specify here? Because what they would need to say is, that there's a hinge here. And this rod is free to rotate about that hinge. Because what if the pivot or the pole, what if the pole was like welded to a metal structure or some object embedded in the building, or just hammered in there? Then you might not even need the cable. So I think it's understood that without the cable, the pole would be free to just flop down. Okay, so how heavy can that sign be? And of course, this mimics real life problems where you'd have to analyze these things before constructing something to make sure that the cable doesn't break and drop the sign on somebody's head, and then you have a big lawsuit. Now, obviously, this is a static equilibrium problem in which we're going to argue that the translational condition is satisfied and the rotational condition is satisfied. So some of the forces is 0, some of the torques is 0. Well, some of the torques on what exactly? Are we looking at the torque on the signpost or the torque on the pole? The string here, or the rope, cable, I'll call it a cable. The cable is pulling on the pole, not the sign. So the torque from the cable is on the pole. Also, the signpost, it's attached with these little strings here, or additional cables. Those are also acting on the pole. So we're really talking about the equilibrium of the pole. Let's draw some forces. Remember, it does matter where you put the tail of these vectors. The cable is applied, or the tension from the cable is applied at the end here. And instead of T max, I'll just call it T. So it's understood we're going to evaluate this at T max. By putting the tension at its max possible value, we're investigating what the max possible mass is for the signpost. Okay. Remember, I keep saying one of the first things you should do is choose your origin. Well, the natural place would be here. And the reason for that is, number one, if the cable breaks, don't you expect this thing to actually swing down like this? And it would pivot about here if there's a hinge. Also, there's some unspecified forces between the pole and the hinge itself, or the socket of the hinge, however that works. I could call that F sub X and F sub Y. So the hinge has some X component of force that it exerts on the pole and some Y component. The problem is not asking for those, but we could go back later and solve for those. And the advantage of putting the pivot here, or the origin here, is that the torque about this point due to these forces is 0. Those forces are applied at the origin, which means the R perp associated with those forces is 0. So we don't even have to worry about those torques. Okay, there are arguably 3 more torques, because don't forget about gravity pulling down on the pole. Let me kill this fly. I think he heard me say that, so he's evading me. I was talking about the torque due to the weight of the pole itself. So as far as gravity is concerned, when you compute torques, you imagine that the gravity force is applied at the center of mass. So the weight of the pole would be applied at the pole center of mass. Now, if this is 200 centimeters, the halfway point is, well, truthfully, it's here. But I'll scoot it to the right just a little bit to keep it away from that, so the diagram's easier to interpret. So here's, I'll put WP, the weight of the pole, because I've specified that the pole's mass here, 5 kilograms. And arguably, there are 2 additional torques on the pole. You see how the sign is being suspended by 2 additional little cables here? So this cable is going to pull down, and this cable is going to pull down. Now, you could be really pedantic and write F equals ma for the sign and conclude that each tension must equal half the weight of the sign in order to specify that tension, but that's fairly obvious, I think. So we're just going to assume that the tension here pulling down on the pole is half the weight of the sign, half the weight of the sign, and that's going to be in terms of the unspecified maximum mass of the sign. Now, because of the numbers given here, we can determine where those torques are applied. Here's where you have to take some liberties here. If you look at the drawing carefully, these strings are not actually right at the edge of the sign. They're displaced a little bit inwards, and they didn't tell you how much. So don't stress about that and think, oh, great, is it 80 centimeters plus another inch? You're just supposed to take the points of application as the left and right ends of the sign. So this little tension's pulling down 80 centimeters from the pivot, and this one would be the full, what is that length? 120 centimeters. I'll put L equals 120. So we know that that the magnitude of the R vector for this torque is 80, and the magnitude of the R vector for the torque due to this little cable would be 120. Okay. Now, you could do it that way, and I think I will do it that way, but it turns out you can skip that and just imagine that the torques from these 2 little tensions are equivalent to a single torque applied at the center of mass of the sign. Because to me, that seems more intuitive. Just imagine that there's a single pull on the pole due to the weight of the sign, and it's applied at the sign's midpoint. But what I'll do is I'll do it the first way by looking at the torques due to these individual tensions, and then show that within that expression is the formula for center of mass. So let me draw some additional little forces. I guess I'll call this, I don't know, F1 and F2. So I've used the letter F a few times. This is just F with components. Over here, I've got F1 and F2. All right, and I think what I'll do this time is, in fact, to make a separate diagram that's a little less cluttered that will help us visualize the torques. And I'll make this one large. So first, let me draw. I'm just going to represent the pole with a single horizontal line. Here's my origin. And I've got a variety of forces here. I'll draw the vectors in marker and label them in pen. Okay, this is the gravity force on the beam, or excuse me, the pole, weight of the pole. This is the tension in the cable. I've got angle theta, which is to be determined. They gave that to us indirectly. And then I've got this downward force from the sine, F1. That's the leftmost piece of string. And then F2 on the other side. And they should be equal in magnitude. I think that's it. You know, I could combine the X and Y components of the force of the hinge on the pole and just call it F, and that's not given in the problem. We could find it if we'd like. And I think that's it. If you want to label distances now, well, this is out. If the pole is, we were told 120 centimeters, then the midpoint of the pole is 60 centimeters out from the pivot. And let's look at the diagram again. The left edge of the sine is 80 centimeters from the pivot. So we know that the R vector for this tension on the left side of the sine, that has a length of 80 centimeters. Now, wait a minute, what am I doing here? 60 centimeters and 80. Don't I have these backwards? Did your book? Oh, I goofed. Okay, it's, of course, the pole, it's right here. It's in my drawing. The pole is 200 centimeters long. So this is 100, excuse me. The midpoint of the pole is 100 centimeters. The 120 centimeters is the width of the sine. How about I call that L? I don't want to use W because I'm using W for weight. Okay, fine. So the width of the sine is, in fact, 120. Okay. I think that's all the distances we need, except for this overall distance of 200 centimeters. Well, this drawing was supposed to be better, but it's quickly devolving. Let's find theta first of all, because we're going to need that. Look at this right triangle here. We've got an opposite side and an adjacent side, so that should be the arc tangent of, I'm going to chop off the zeros. This is 25 over 20. Let's see what that is. 25 divided by 20. I'll take the arc tangent, 51.3. I feel like that same angle just came up in a different problem. Did it? Okay. And then when it comes time to write the torque equation, well, look how easy these forces are. I'm extending their lines of action. And this vector has been drawn so long, I don't even really need to extend its line of action. So if we're going to go with this means of calculating torque, torque equals R perp F, that makes it really easy for these forces. This is the weight of the pole, the tension on the left side of the sine. Those are easy because this distance out along the pole is already perpendicular to the line of action of the forces. So it would be easiest just to use R perp F. Now, when it comes to the torque due to the tension, the distance from the pivot out to where the tension is applied, that line segment is not perpendicular to the line of action of the tension. So we would, in fact, need to do this. This would be R perp for the tension. And we can use trigonometry to find this distance. But what I'm going to do instead is just go with this means of calculating torque. R F sine theta. This is the general theta between the R and F vectors. Now, in my picture, I used theta specifically for this angle right here. but that's actually the angle that we want anyway. So remember, the R vector for any particular force goes from the pivot to where the force is applied. So for the tension, it's applied at the right end of the pole. This would be the R vector. So this is the angle that we want. And since I've just found that angle, I can simply use this formula to find the torque. That's what I'm going to do. So let me write all these equations now, the conditions for static equilibrium. First, we'll start with some of the forces in the y direction must be 0. Remember, we're trying to find the maximum possible weight of the sign. And I want to make one more point here before I do that. I said a moment ago that it's fairly obvious that the tension here has to equal the tension here. That's only because of the symmetry of the problem. That's not always the case. What if the sign was hanging at some weird angle like this and you had strings of different lengths? You can imagine that this tension might be different from this tension. Maybe it should be obvious to me which would be greater, but I'm not really sure. So it's only because of the symmetry that we can argue that F1 and F2 have the same magnitude, and that magnitude would be half of the weight of the sign. Okay, so when I look at my picture here, let's go with, I'm actually going to go with this picture. I could resolve the tension into components. Okay, this would be T sub X, this is T sub Y. Now T sub Y, the vertical component, that would be T sine of theta. And I'm already seeing here, to solve the problem for what they ask, we don't even need to write this equation, but let's get the practice anyway. Plus the unspecified Y component of the hinge force minus the weight of the pole minus, now we've got F1 and F2, but each of those is half the weight of the sign. So when we add those up, we just get minus the weight of the sign. That's got to be equal to 0. So how many unknowns do we have in this equation? We don't know actually we do know. Remember, they specified that the max tension is 300. So these are both known. We don't know the vertical component of the hinge force on the pole, and we don't know the unspecified weight of the sign. So this equation has two unknowns. We cannot get the answer to the question or the problem by using this one equation. They were asking for the max possible weight of the sign. We cannot solve this equation for weight of the sign because we also do not know the hinge force. Moving on, the sum of the forces in the x direction also have to be 0 if this pole is going to be in equilibrium. Well, I see the horizontal component of the tension jamming the pole into the wall. You see that? The greater this tension, the more the string or the cable tends to jam the pole into the wall. And that means the hinge has to push back with the force Fx. So I could say this unspecified force Fx to the right minus T cos theta would have to be 0. And again, we know the angle. We know the max possible tension. So we could actually solve this equation directly for the horizontal component of the hinge force. However, the problem is not asking for that. Do you see how this equation does not contain Ws, the weight of the sign? So there are actually 1, 2, 3 unknowns between these two equations. I cannot use F equals ma alone, the translational condition, to find the desired quantity, which is the weight of the sign. And now you know we have to move on and write the torque equation. There's no way around it. The rotational equilibrium is necessary to solve this problem. So we'll say the torque net must be 0. Because I'm putting the origin here, I don't need to worry about the torques from Fx and Fy. They have a moment arm of 0. But I do need to take into consideration the torques from this force, this force, this force, and this force. There are arguably 4 torques. There's the torque from the left cable that hangs the sign. There's the torque from the weight of the pole. There's the torque from the right cable. Remember that little extra cable? Look at the picture in the book that hangs the sign. And then there's the torque from the main cable itself. 4 torques that have to sum to 0. So I could say, I'm gonna do it this way. I'm gonna say torque due to the weight of the pole, the torque due to the leftmost little short cable hanging the sign, and the torque due to the rightmost little cable hanging the sign, plus the torque due to the main cable. I hope you're not confused by these different cables here. You'd have to go back to the picture Now it's all cluttered. Check out the picture in your book. There's actually 3 cables, but 2 of them are just tiny little cables between the sign and the pole. Okay, if these are to sum to 0, then at least one of them must be 0. And now we just use the two possible ways that we have for calculating torque. As far as this force, and this force are concerned, the easiest expression would be to use the r perp f because they're already perpendicular. All the r vectors go out like this along the pole, and all the forces are perpendicular. So there's no need to use trigonometry. Okay, what are the signs of these torques? Well, they're all downward pulls. So the torques about this point would all be clockwise. All 3 of these get a minus sign. So I'm going to say minus. Now, what is r perp? This time I'm not going to write r perp f, r perp f. I'll just evaluate them directly. What is r perp for the weight of the sign? It's the distance from the pivot to where gravity is applied. That's the midpoint. So that's merely the 100 centimeters. And I guess I'll go ahead and plug in numbers now. Oftentimes, I like to use symbols as far as possible and then plug in numbers at the end. But I'm going to go ahead and plug in the 100 centimeters. Now, here's another point. Is it necessary to convert to meters? Actually, no. As long as you're consistent. If I'm going to use centimeters here, I better use centimeters throughout. So in other words, I'll be computing torque in units of centimeter Newton or Newton centimeters. 1 Newton centimeter is 1 Newton times 100th of a meter, which is 100th of a Newton meter of torque. So it's not the SI unit of torque, but that's okay. I think this would be easier than converting. It really doesn't matter. I mean, the safest thing always would be to convert. Okay, so I've got 100 centimeters times the mass of the pole times g. And again, if I use 9.8 meters per second, this would come out in newtons. And then centimeters, I'd have torque in Newton centimeters. All right. Now, where is F1 applied? 80 centimeters out from the pivot. So minus 80 centimeters times 1/2 the weight of the sign, which is mass of the sign times G. I suppose you could just call this WS, call MG WS, and at the end, convert from weight to mass. Remember, weight is mass times the G field. So if you solved for the weight in newtons, at the end you would have to divide by 9.8 to convert back into mass, right? Newtons over 9.8 would give you the mass in kilograms. Okay, now where is F2 applied? That's out here at the full 200 centimeters. So minus 200 centimeters times half the weight of the sign being supported by that cable on the right. And then the very last torque, well, think about it. If you were tugging in this direction on the end of the sign, wouldn't that tend to, or on the end of the pole, wouldn't that tend to rotate the pole counterclockwise? So that's the one positive torque. So I'll say plus, and I'm just going to use RF sine theta. So R, that's the distance from the pivot to where the tension is applied. That's the full length of 200. And then the F is the max tension, the 300 newtons, which I'll plug in at the end, and then times the sine of 53.1. Yeah, so I'm plugging in numbers sometimes and not other times. It's kind of a mixed notation here. Normally, I like to do everything with symbols and then plug in stuff at the end. Okay, is this the one equation that we can solve for the mass of the sign? That looks to be the case because we do know the mass of the pole. We've evaluated all the distances. It looks to me like the only unknown in this equation here is the mass of the sign. So again, by evaluating T at T max, evaluate at the max value, then you're really solving for the max possible sign mass. Okay, now before I actually solve this directly or solve for X, no, MS, I'm solving for MS. I want to show you that this really tells us something familiar about center of mass. So this says negative 100. And I'll go ahead and plug in the mass of the pole. That was 5 kilograms, 9.8. Again, kilograms times meters per second gives us newtons. And then I've got centimeters. So my torque is coming out in Newton centimeters. And let's see here. I'm going to factor out the negative sign here. And I'm also going to factor out G. So watch this. I've got 80 times ms over 2 plus 200 times ms over 2 times G. And you don't have to do it this way. I'm doing it this way to show you something that's rather intuitive. Look at the sign. And imagine in your mind, chopping the sign into two pieces, one of which is here and one of which is here. So I've got half the mass of the sign, arguably, at 80 centimeters, and the other half of the sign is out at 200. So I've taken that coordinate of 80 times half the mass of the sign, plus that coordinate of 200 times half the mass of the sign. Isn't that the definition of center of mass? So this would really be, this is equal to the x coordinate of the center of mass times the total mass of the sign. I'm using the definition of center of mass. And then what I've actually done, once you take mass, times G, that's the weight. So I'm calculating the torque, whether you realized it or not, excuse me. I'm calculating the torque as if the full weight of the sign, MSG, is being applied at the center of mass of the sign. And that was my impulse at the beginning, was just to not worry about these little tensions and say, hey, the sign is pulling down on the pole right here at its midpoint. And that would be, let's see, the sign is 120, so half the sign is 60. 80 plus 60, that would be 140. I would just say that the sign is pulling down at the 140 centimeter mark with a force equal to its total weight. And that would work. Maybe this is safer the way we're going about doing it. Okay, I'm going to pause and calculate the mass of the sign. You should do the same. Okay, what I did was combine these terms. I evaluated G at 9.8. I evaluated the tension at 300. I shifted some stuff around. I plugged in the 5 kilograms for the mass of the pole. And I find that the max allowable mass of the sign is 30.6, just like the book got. Now let's think about cause and effect here. If you chose a more massive sign, like 50 kilograms, then these tensions F1 and F2 would have to increase in order to support the weight of the sign. And that means these clockwise. These clockwise torques on the pole would increase. Remember, these little tensions are pulling down on the pole in such a way that they would tend to make it rotate clockwise. So if the clockwise torques due to these little tensions increase, that means the counterclockwise torque due to the tension in the cable would have to increase as well so that the torques remain balanced. And that means immediately the tension in the cable would shoot up above 300 newtons and presumably it would break. So that some of that, or maybe all of that, is pretty intuitive to you, but it's nice to be able to understand that or be able to express that using these conditions for static equilibrium. Now, since we've determined the max allowable mass of the sign, we could go back now and figure out what the tension or what the hinge force would be for that maximum mass. So if we went ahead and put a sign on the pole that was 30.6 kilograms, whatever it was, we could go back to the translational equations. Actually, this one we're already done. We just evaluate 300, 51.3 and find fx. Then we go back here and we plug in the mass of the sign that we found, and we could solve for fy. Once you've got the components of the hinge force, you could use Pythagorean theorem to find the magnitude of the force within the hinge. And you can imagine that would need to be fairly sizable, right? Because all these forces on the pole in some sense have to be balanced by the hinge. And what you could do is, in addition to finding the strength of that overall hinge force, is also find the direction. depending on the arctangent of Fy over Fx, you could figure out which direction the hinge has to push on the pole overall. That really wouldn't be difficult to do. You would just need to revisit the translational equations. Okay, so this is a good problem because you do have to use a couple formulas for calculating torque, or at the very least, it's more difficult than the previous problem where everything was perpendicular.